So in this video we're going to study the features of logarithmic functions. Now there are many logarithmic functions, right? Log of x in any base b is a logarithmic function, and b can change, but b is positive, but depending on whether b is between 0 and 1 or above 1, the graph is going to be slightly different because the graph of the exponential is different in that case. But luckily for us, we don't need to focus on all the graphs of logarithmic functions. At least I don't think they're all that important. The ones you want to really remember are log in base 10. And remember, log in base 10 is simply written down as log of x. And log in base e. Log in base e is just written as ln of x. So we're just going to study those. And in both cases, the base, whether it's 10 or e, is above 1. So the features of those two graphs are about the same. So we're going to start with the graph of y equals log of x. Okay? And to study that graph, we're going to study the graph of its related exponential function, which is y equals 10 to the x. Now 10 to the x is an increasing exponential function like that. Okay, and like all exponential functions where the coefficient of the power is 1, it goes through 0, 1, because 10 to the 0 is 1. So to get the graph of our exponential function, we just need to reflect that graph across the line y equals x, and therefore we're going to get something that looks like this. Now notice how the exponential function has a horizontal asymptote, and that's going to be converted into a vertical asymptote for our logarithmic function for log of x. And it's going to go through 0, 1. Okay, so I'm going to write down the different features. So maybe let's call that f here. So that would be the inverse. So the log is the inverse of the exponential. So let's look at the features of f. Okay. What's the domain of f? Well, if I look at the graph of the exponential function, it has a y value for every single f. So the domain is just all real numbers. Okay. Now for our inverse function, okay, the domain turns out to be the range of the inverse. So the range of the logarithmic function is going to be r. So the range of our log function, or inverse function of f, is going to be all reals. And you can actually see this because the logarithmic function, you can actually see that it covers all possible y values, right? It goes all the way to minus infinity as you get closer to the vertical asymptote, and it goes to infinity as you move away from the origin. Now what's the range of the exponential function? Well, the range are the y values that are covered by it, and we can see that the exponential function, its graph lies completely above the x-axis. So the y values that are covered are all those positive y values. So the range will be anything above 0, all positive values. So that's going to be the domain of our log function. And we can see it. The logarithmic function only has a curve that's to the right-hand side of the y-axis. What else? We can look at behavior at infinity. So for the exponential function, when x goes to infinity, f of x also goes towards infinity. That's because the base, which is 10, is above 1. We also have the behavior at minus infinity. When x goes to minus infinity, f of x goes to goes where? It goes towards 0, right? Because the values of x are getting really close to the x-axis as you move towards minus infinity. So for the inverse function, you just have to revert those. Okay, so let me convert this one. So when x goes to, so instead of So well, actually, let's start with the other one. It's going to be a little more clear what I want to do here. So here we're going to have to invert this. So instead of writing f of x goes to 0, I'm going to write when x goes to 0, then f of x, then f inverse of x, or log, is going to go towards minus infinity. And we see this, right, because of this behavior here. As I get close to 0, the log gets close to minus infinity. So for the other part, it's actually a lot easier because both are going to infinity. So I could just write when x goes to infinity, then f inverse, the log, goes to infinity. So that's why I finished with that, because it would not have been so obvious that I just, this inverse here, this infinity here, is the one that's here. Right? But then since they're both infinity, this one is the one I replace here, but they're both infinity, so it just comes down to infinity for both places, where here, when x goes to 0, you can actually see really that this 0 went there and this minus infinity went here. They were inverted in some way. Okay. Here, for f, we've got an asymptote, which is the y-axis. As you can see on this curve, it gets really, really close to the x-axis. Did I say y? It's the x-axis. As x goes to minus infinity to y equals 0, which is the x-axis, is a horizontal asymptote. Okay, now we're going to change this. We changed the roles of x and y, remember, for the inverse. So now x equals 0, which is the y-axis. Maybe I should write that. This is the x-axis here. X equals 0 is the y-axis. Is now, instead of being horizontal now, it's a vertical asymptote. Is a vertical asymptote. Okay, and the same is going to be true for ln of x. So ln of x is sort of similar, because e to the x will look like this. So ln of x, once again, will look like that. So that's why I was telling you, log and L of x and ln of x have very similar features. So, so this is something you have to remember, but note that as long as you know how the exponential function behaves, you know exactly how the log behaves because of the symmetry.